In 1874, a young student named Max Planck approached his professor, Philip von Jolly, to ask about a career in physics. The professor's advice was dismissive. He told Planck to pick another field, because almost everything is already discovered, and all that remains is to fill a few unimportant holes. This advice captured the confidence of the scientific establishment. They had built a towering intellectual machine out of 4 core pillars: mechanics, electromagnetic theory, optics, and thermodynamics. These disciplines locked together to explain almost every observable phenomenon. To the great minds of the late 19th century, their framework was complete. Future generations were expected to simply tidy up the margins. The architects of this fortress were entirely unprepared for a small, everyday anomaly sitting in plain sight, one that would bring their entire structure down. The anomaly was a common part of everyday life. When you heat up a furnace or the coals of a barbecue, the objects emit a characteristic red glow. In physics, this is known as black body radiation. The challenge presented to the establishment was simple: use the rules of thermodynamics and electromagnetism to provide a mathematical explanation for that red light. When they applied the old equations to the problem, the mathematics collapsed entirely. This chart reveals exactly where the models broke. Looking at the black line representing classical theory, you can see that a glowing object shouldn't emit a steady, finite amount of light. Instead, the math predicted that it would emit an infinite amount of energy. This became known as the ultraviolet catastrophe. That simple glowing coal proved the classical equations were disconnected from reality. The bedrock of 19th century physics was broken. Ignoring his professor's advice, Planck moved to the University of Berlin. He didn't want to start a revolution. He said he only wished to understand the known fundamentals of thermodynamics. But by December 1900, Planck realized those rules could not be saved. To match the actual measurements, these precise, colorful bell curves, he had to abandon classical frameworks. He proposed an idea so counterintuitive that he called it absurd. For centuries, scientists believed energy flowed in a smooth, continuous stream. Planck suggested that energy is instead released in distinct, quantifiable chunks. He called these chunks quanta. The size of these packets was governed by a fundamental unit of scale known as Planck's constant, represented by the letter h. By finding the only mathematical solution that fit a glowing piece of coal, Planck inadvertently dismantled classical physics and laid the foundation for quantum mechanics. While the world of apples and planets follow predictable rules, the microscopic quantum realm proved to be entirely different. At the quantum scale, basic human concepts start to break down. Even the idea that an electron has a definitive position or moves along a clear trajectory ceases to make sense. Consider an experiment at Bell Labs in 1927. While firing electron beams at a nickel target, scientists Clinton Davison and Lester Germer watched as the electrons formed a clear diffraction pattern. Solid matter was behaving exactly like a wave. This confirmed wave-particle duality, the fact that the boundary between solid particles and radiating energy waves vanishes at the microscopic level. To describe reality at this scale, science was forced to permanently move beyond human common sense. Planck's breakthrough triggered a cascade of discoveries. In 1905, an obscure patent clerk named Albert Einstein proved that even time is relative, ticking at different speeds depending on the observer's motion. The old world order was gone. By 1932, Carl Anderson identified positrons, confirming the existence of antimatter. In 1936, researchers discovered the muon, a particle so unexpected it prompted the physicist I. Rabi to ask, who ordered that? This map of quarks and bosons, the Standard Model, represents our modern understanding of matter. It shows a level of complexity that 19th century physicists couldn't have imagined. Yet, even with these tools, we now admit that we understand at most 3% of what we observe. We are currently ignorant about 97% of the universe. Professor von Jolly was spectacularly wrong. By investigating one unimportant glowing coal, Max Planck showed that the most intensive period of scientific discovery was actually in its infancy.